In this video, we will see how we can apply quasar software to correct spectra taken under ambient pressure. If we take an XPS spectrum from a surface, we do that in vacuum, and we get, in this case, from gold, from a pure gold foil, we have this spectrum. If we introduce a gas, we have energy loss processes as the electrons are transported from the surface up to the spectrometer. And we get a distorted spectrum where we have peaks in the spectrum which correspond to excitations of electrons in the gas. The data I'll show here is from Mark Greiner's group at the Max Planck Institute in Mülheim. We published together a paper on this, which you can find here in this reference. So the aim is to remove the distortion from scattering in the gas and bring this spectrum back to what it looked like at the surface. Now we have an inert surface here, gold, and the nitrogen gas, so we assure that no distortion takes place of the spectrum at the surface of the gold. As the electrons, the photoelectrons leave the surface, they'll be the same. So we look for a method to go from this spectrum and back to that spectrum. As a function of gas pressure, of course, the effect of the gas increases, and we'll look at these. This shows how the cross-section is constructed. I'll not go into detail of that here, but in the following video, we will go through all the details needed to construct the cross-section used to correct the spectrum. So we use the external facility for the external cross-section and put in different peaks there. And finally, we end up with a cross-section where all these peaks correspond to excitations in the gas. And when this is applied with the quasar software, we can go from this spectrum and back to this, where we have compared it to the pure gold spectrum. So the background corrected spectrum is equal to the pure gold spectrum to within the noise level, practically. So it seems to work very well. Now, this is the cross-section we applied. Now, if we apply this to all the different gases, we would expect it to, or we hope that it would work for the other gas pressures as well. So the only thing we vary here is the effective thickness of the gas. So this is the analysis of the spectrum at 5 millibar, and here are the other ones. And in each case, you see, by just varying the effective thickness of the gas, but using the exact same cross-section, we end up with a perfect correction of the spectrum for the effect of the gas. Now, we would expect this effective thickness that we determine here to be proportional to the gas pressure. And here, this is plotted, the gas pressure here and the effective thickness. And you see it's a very, very linear, to within 1% or so, it is directly proportional to the gas pressure. So the conclusion of this is that we can find a way to remove the distortion of the spectrum caused by the transport through the gas. Once this has been determined for one case, like gold here, the same cross-section can be used for other situations. We'll see in the following video, we'll see how we go about doing this in detail. So now we will go through the steps needed to do the analysis. First, the creation of the cross-section for the nitrogen gas, and then the application of this cross-section to correct the spectrum for the effect of the gas. So here is the data. I have the data here in in this example here, number 17, Amb XPS. And the spectra here, gold in vacuum is the first one here, and then increasing pressures here up to 5 millibar. I've already taken these spectra and removed the background, the continuous background here in the usual way by, show that by example here. We go through the correction here, so we transmission correct, and then isolate the peaks by zooming in the usual way and putting in a background line here which fits over on this side, and subtract that and save it. Already did that for all the spectra, so that's the TXT core version of the files out here. So now we look at the spectra. We have the vacuum spectrum is here. We have like at 3 millibar nitrogen, we have these peaks showing up, and they of course increase as the gas pressure increases. So this is the aim now, to remove these backgrounds. So we do that by analysis with the software. So to analyze the spectra, we use analyze, and we just want to remove the effect of the gas and bring the spectrum back to what it was at the surface without the gas. To do that, we need a structure which corresponds to having a situation where spectrum is transported through the gas, and want to remove that effect on the spectrum. This can be done by the several buried layers software here, possibility. By the way this is done is by choosing the thickness of 1 angstrom and then varying the depth. What this will do is that it will take the spectrum from this assumed layer here, which is transported through the gas, and it will remove the effect of the gas and bring the spectrum measured out here back to the spectrum as it was here at the surface. So this is a procedure, fairly straightforward. You put in a 1 angstrom width, and then you vary the depth. The depth is then the effective thickness of the gas. The effective thickness of the gas depends on the IMFP. The IMFP of the gas is probably on the order of 1 millimeter, but I've chosen here an effective IMFP of 100 angstroms, 10 nanometers. It doesn't really matter what you choose, because all the depths will vary linearly with the IMFP applied here. So we start with the analysis. You see it here, and of course the universal cross-section is not good. We need an external cross-section, so we choose this possibility, and then we have these peaks here, and the first peak, I mean, these corresponds to excitations in the nitrogen gas. The smallest peak here is about 13 eV down. And then you have this excitation, and you also have on top of that, you have excitations to a continuum of states. So how do we handle that? We take a cross section, a fairly wide cross section. Let me put in 600 here for the position, and fairly wide, maybe 1100 here. This gives a very broad distribution here to model the effect of the excitations to the continuum. We put in a gap, because we will have no excitations up to about 13 eV to the continuum, and after that we have this excitations. And so we just take this one here, and let's just see if we move this to 50 here. Let's see what happens. It seems to work fairly well out here. We don't want to go all the way back to the background here. We want it to be the corrected spectrum needs to be the spectrum in the vacuum. So let me show you. If we take this as the reference, we click up here, and now it's compared to the spectrum. Put this out here so it normalizes the peak intensity here, and you see the background is more or less correct here. So this is a good choice to correct for the continuum out here. So we take this, and we now save this cross section. So we save it, and where do we save it? We give it a file name first of all. It's the U3 3-parameter cross section. We have the parameters 600 and 1100 for C and D, 600, 1100, and a gap of 13. So we save this, and we find a place to save it. I created a folder here with X sections. So we'll put the cross sections in here. So I put them in here, I save this up here. So now we have this one. Next. So now we start to worry about the sharp peaks here, which corresponds to excitations of electrons in occupied states to unoccupied states within the gas. Some very sharp peaks. So the width is fairly small. We put in an energy gap now of 0. We put in a width here of 1 maybe, and then we try to line up the peak to what we have measured here. So it's here. It's this peak here corresponds to that peak. We need to diminish the weight of this one. We will adjust the weights later on after we've created all the cross sections, so we don't worry about that. Only the width and the position of the peak matters at the moment. We need to move this further out, and this is too much. 200, 150. Change this to 5 and vary this. So it's about here. See, it's too far out here. And at 70, it's close to the right position, but it's too wide here. It needs to be much smaller. So I put in a 0.1, and we decrease the width of the peak. It seems to be even less than 0.1. So I put in now a 0.005, and we decrease this. And let's try with something like this. This is about the right width here, corresponding to what we have measured. We could increase this a little bit to 0.25, so we get a bit higher weight. And now we can see what the negative excursion is here. You see, now it's pointing up here. We're too far out, and here it's too low. We have this negative excursion. So we fine adjust now with a 1 here, and you see here we have a smooth transition here. So this is the right position of this peak. So now we give this a name, we save it, and that's a U3 cross section with 172 for C and 0.025 for D and 0 for the energy gap. So I want to save that up here. So I click save, and now we have that. Next peak is here, and this lines up with that peak, or it corresponds to that peak, because we have the 2 peaks here. So we have these 2 here from this and that. This one will give rise to a peak over here as well, corresponding to these 2 peaks. So we now line up the last peak with this position. So we need to increase this. Let me put in a 5 again here, so we go out, and we have it about here. So now again, let me reduce this a little bit so we can see what's going on here and here. These are the two regions we worry about. I put in a 1 here and vary this. You see here, we start to see a peak coming up here. We want a smooth transition there. So that's about here. And now it's going negative here. So 204 is a good number. So we save that as well. So that's now a 204, 0.025, 0, and we save that as well. So now we have these three cross sections, and you see this peak takes care of this peak and takes care of that peak, takes care of these two peaks more or less. So we have multiple scattering here, double and triple. So we're left now with the peak here that's not accounted for. And this doesn't have a corresponding peak out here corresponding to these two. So this must be the peak that corresponds to this peak, whereas the other peak corresponds to that will be in here somewhere, so we don't see that clearly. So we just fit to this peak out here. And this is further away again. Put in a 5 here, and we move this out. And now it's this peak here, we want to line up with that. And it's about here, 260. I can increase this so we can see where it is. And you see it lines up very nicely here. The correct weight will be something like this, maybe, where you see now it's removed here. But we fine adjust the weights later on. So it takes care of this and some small peaks here corresponding to double scattering and triple scattering. So we save that as well. So that's now at 260. C was 260. The width was the same, sharp peak and 0 there for the band gap. So now we have these 4 cross sections to play with, and we will then make a combination of these to account for the full spectrum. So we'll now make a linear combination of these cross sections to account for all the excitations in the gas. To do that, we choose blend of cross sections, and we load these cross sections. So it tells us to read a file, X section 1. So we read this file and we load it here in X section 1. So it's here now. Click here to get cross section 2. Click OK. Click here and load it. Number 3, click OK. Number 3 is here. We load it here. Number 4, OK. It's this one. We load it here. So now we have different weights here on the cross sections. The program works in a way that if you change one of these, it will renormalize the other ones to always give a value of 1 here. We don't want that because we want to have full flexibility to change the relative weights of them. So we click here to not automatically renormalize the weights. So we start by putting in weight 0 for these things, the smaller peaks here, and we have just the continuum of excitations. We'll first find a reasonable value for the depth to get the weight of this one roughly correct. So if we put in a weight of 0.75, we have 0.25 to these weights, and with that weight we can find the depth that would give us a good account for the general background here. Seems to be a bit higher than 200. Maybe it's 250. We can see that in more detail if we load now the spectrum from in vacuum. It's this one. So now we want to compare these. I move this out here again, so it normalizes the spectra in this region. So we have about 250. There's a little bit left here, but there will be some multiple scattering from these peaks. So let's just keep it at 0.75, and we can make fine adjustments later if needed. So now we start to put on weights here for the first cross section correspond to this peak, and it's about here, 0.1 here. We have the increment here. When I click here, this is the increment. If I put down 0.05, we see that it's about 0.11 here. This is a little bit too little, and this is a little bit too much. So 0.11 here. Take the next cross section correspond to that peak. Click up here, and what do we get? We get about 0.55. So now it's fairly smooth in this region as well. We have the peak out here, number 3, and we increase that. And maybe this is too much. It's about here. It's very close, smooth everywhere here. You could make fine adjustments of these values to get a little bit better account. You could also put in a small peak here. I'll not do that here, but you can do that. We can check what happens here for the other thicknesses. Here we have number 5, that's with 5 millibar. If we take number 3, we would expect the thickness here to be different. Let me put this at 50 here, and you see that it's about 150. So that's a smaller effective thickness. For 2 millibars, it's smaller again, and you can fine adjust the thickness here. This is too much, and maybe here, or 95 is probably the right one, and for 1, it's smaller again. And this is the plot. If you plot these effective thicknesses towards the gas pressure, it comes out to be very linear. So this, as we have seen, gave a fairly good account for the effect of the gas. Put this in again, 250 for the 5 millibar gas pressure. If you want to go on and account for this peak here and maybe small peaks out here, the way you do that is you first save this cross section, because this works fairly well. So we save that and give it a name. We could call that U blend blend 1 maybe. So we have a cross section U blend 1 that's here. So now what we do is that we start all over again here. So we take cross sections again. Now we take the first cross section, we just take U blend 1 and load that in here. And we put in a weight here of 1. Because this is what we found before. We take the full U blend 1, which we just saved, and this works fairly well. To account for this peak here, we need a new universal cross section, a new 3-parameter cross section, which should be about here. And I just change the position of this. Maybe it's about 100. We have an increment of 2 here, so I move this down. So it fits more or less here. here. It fits more or less there. We can see if I change this. So this is where the small peak is. It needs a very small intensity here, but here it is, about 1 or 2 here. But we'll adjust this weight, of course, later. So just save this along with the other ones. Use your way and save cross section. And now this is U3 of what's 88 and 0.025 and 0 for the band gap. So now we have this, and we can go back and make a blend of cross sections. First one is U blend 1. We did that already. Now we take another one, which is not this one, but it is the new one we just created here. So I load that in here. And now we see the effect of these. We go back to 250 here and see that it counts. So you fine adjust the weights here, and it can take a little time to do that. But once you have done that, you fit in peaks by peak here, and then you can save this as a new blend of cross section and add more on top of that. I have done that here in this blend 7. So if we load that in here, take just one, we take a weight of 1, and then as you'll see here, if we fine adjust the thickness here, it takes care of all the excitations here. And you can see I put in a peak here, put in a peak here, and maybe one more peak out here, forgotten. This cross section, I call that blend 7. And let's just see how it works if we take with the spectrum in 2 millibars, and that's about 100, I think. Yes, we can fine adjust now the depth, and you see this is too much, and here it's perfect. Do that with another one in 4 millibars, and you find again a new thickness, effective thickness, which is about 220, and it takes care of all the fine structure here in the spectrum by adding these 2 small peaks.